Okay, so what metals do, right? So let's say, for instance, this green metal here is going to be our sodium, right? So if that's sodium, so what sodium metal does, it'll actually just drop its electron. You see that electron there? Right next to it. And be like, oh, whose electron is that? Oh, that electron is negative. Guess what? Now I'm positive. So we're interacting, right? Even though it's its own electron, it'll try to play this game, so it would have a plus and a minus charge. Okay, so this is what is called delocalized electron, because they're actually just dropping that electron, and they kind of form like what we call a sea of electrons. So you have that positive and that negative and that positive and that negative, because you just have those electrons that are there available, right? And it makes that metal seem as if it's stable like it wants to be, right? Because sodium wants to get rid of that one electron. Although it's not truly gotten rid of it, it just pretends it does. Okay, now this allows other metals to come into that sea of metals and electrons and put themselves in there. And we're able to sit there, use this to our advantage to sit there and form alloys. And so we can form metals that are composed of different other metals at different concentrations. And they're able to sit there and interact as if they're totally solid and they belong together, like really belong together. Like for instance, how many of you guys have gold jewelry? Erica, wake up.
Yes.
You got gold jewelry, Erica?
No, this is Alex.
Oh, Alex, you got gold jewelry, Alex? Is it 24 karat gold, or is it 18 karat gold? Or is it 12 karat gold? Alex, what was that? It's 18?
I'm not sure. I got it as a gift. Like I picked it out with my mom and dad, but then ended up getting it for me later on for my birthday. I think it's 12.
12?
Yeah.
Okay. So in that case, well, 24 karat gold is pure gold. 18 karat gold, so let's take a look. 18 karat gold is 75% gold, 12.5% silver, and 12.5% copper. So 12% gold is going to be less gold, and then you're going to up those other two. Okay? So if you have rose gold, so that's going to sit there and be gold, and it's going to be silver, and it's going to be manganese, right? To give it that little red color to it. So we can use these alloys to our advantages. So if we want something that's a certain color, a metal that's a certain color, we can use a different metal to sit there and add to that color, right? Like I said, manganese gives you that red tint. We have brass, which is like copper and zinc. We have bronze, which is copper and tin. We have carbon steel, which is a very strong form of steel. That's just carbon and iron. We have pewter, which is tin, antimony, and copper. So depending on what we use, we can sit there and make improvements to the metal, like in the case of stainless steel, right? That's 70% iron, 20% chromium, and 8 to 12% nickel. Well, we know that iron rust, but addition of chrome keeps the iron from rusting. So just having those small bits of chrome there will keep it from rusting. So that's why we call that stainless steel, right? Because it doesn't rust. Okay, so we take advantage of the ability of these metals to delocalize their electrons to sit there and form alloys. And those alloys can be beneficial to us in society, right? Because nobody wants your car. Do you want your car to rust out at the bottom?
No.
No. Yeah, see, that used to happen a lot in Cleveland when I lived in Cleveland. A lot of people's car would rust out at the bottom because they used cheap steel at the bottom, and it just literally the salt would just eat right through it over time. Okay, so that's pretty much it on chapter 12. Chapter 13. Okay, so we've talked about Lewis dot structures. In the lab, we kind of talked about how you go about using them. So these are the steps to drawing your, for doing the Lewis diagram. So when we're talking about the molecules themselves, right? So the one thing that we always want to do is count the number of valence electrons, right? And if there's an ionic charge or an ion, So we need to sit there, either add electrons if it's a anion, and if it's a cation, we want to remove electrons. And so we want to account for that. We want to put the one that is the least electronegative. You guys remember which one is more electronegative? Is carbon more electronegative, or is oxygen more electronegative?
Carbon.
Okay.
Fluorine, whatever's closer to fluorine. I don't have my table.
Oxygen is more than carbon.
So oxygen is more electronegative, right? So if they're on the same line, the one that's closest to the noble gas is going to be the most electronegative. Now, if they're on different lines, we have to sit there and pay attention to their electronegativity. Where can I find their electronegativity at?
That other table.
That table, which, remind me, I need to upload onto your resources, right?
That's
Screenshotted the book and printed it out.
Oh, it's already up there?
No, I said I screenshot the book and just printed it out.
Okay. What were you saying, Iberi?
I was asking if we can have a copy of the electronegativity table.
Yes, you can have a copy of it. I will be putting one up on there,
All right, thank you.
okay, for you guys to print out. So let me put that on my to-do list. Earn $3 million and add.
Dr. Henrik,
Yes.
can I show you the one I have? I don't know if it's the one. Is that okay if I show you?
Let's show me afterwards, okay?
Okay.
Okay, so, and then it's kind of a guessing game, right? So the goal is to make sure that everybody has their octet full, right? So you're gonna play around with it a little bit. And after doing it a bit, it's gonna start clicking. And I promise you it'll start clicking, but you gotta do enough of them to click. Have you guys started it? Can't even talk. Have you started it on CHEM-001?
Yeah.
Yeah, isn't it pretty cool that you can sit there and drag the electrons and all that stuff?
Yeah, but that's the question that Megan has because we drew it like a bajillion times.
Okay, so let's go ahead. Which question was it? Since we're going to do the CHEM-101.
Oh.
Okay, so let's see.
Dr. Henry, are you sharing your screen? Because I can't see anything.
Can't see anything?
Yeah.
No.
Hold on.
Yeah, I can't see it.
I can see it.
Yeah, I can as well.
I can't either.
So
No, Yeah.
Oh, you
they
can?
said
I
that they
can't.
can. So Eric, do me a favor. What you're
Huh?
going to do is go to the very bottom where your menu's at, and you're going to hit the zoom button. It's going to be a camera.
Menu button, camera.
Do you
The
see
very
camera?
bottom?
Yep, at the very bottom.
Where it says start video? Oh, there's not that one.
No, below that, the menu bar. Because,
Oh.
On the dock.
yeah, on the dock. Thank you.
Yeah.
Oh, hold on.
Maybe
This is
log.
I have two monitors open. That's why. Maybe that's why.
Yeah, it could be because one will be on one side and one will be on the other side too.
Oh, I got it now.
Okay, good. Okay,
Thank
so everybody has a periodic table next to them? Periodic table, right? Okay, so how many valence electrons does P have? Capital P.
5.
5.
Okay, so we know that P has 5 valence electrons, so let's go ahead, right? 5 for our P. And then what about O?
6.
6?
Yep.
Okay. And what about CL?
Times 3.
Times 3.
It has how many?
7.
7 times 3.
Times 3.
Okay. Okay, so we add these all together.
32.
32.
32.
So we have 32 electrons to work with,
Yeah.
okay? So, and that's the
That-
answer you put down here?
Yeah.
And that part's right?
Yes, it was
Okay.
I didn't, I have it where it worked out. Like Kelsey said, we've tried it multiple times and I'm not sure what's wrong with mine.
Okay,
All of
so
them.
let's figure out who's gonna be in the middle. Who's gonna be our center atom?
I said oxygen.
No, it's P.
P. P is gonna be our center atom because if you look on our periodic table, let me pull up a periodic table.
But you're unable to complete an octet with phosphorus.
You're able to complete an octet. Remember, electrons are mobile, right? They're not static. They're gonna be constantly moving. And so if they're sharing, you could have all your electrons from phosphorus being shared with whomever. So let's see the table.
CBD chemical formula
What was that?
on your history CBD chemical formula.
Yeah, I had it for a test. I
Oh,
used it for a test.
okay.
Okay, so if we start off with P as our center atom,
Yes, P is the center atom.
okay, and we know that it has
4 bonds.
okay, so you're gonna say 4 bonds.
5 electrons.
So 1 will be oxygen and 3 will be chlorine.
Oops, for carbon. Come on, there you go. Okay, but let me show you how it works by hand, since we don't have a nice, beautiful tool like that. So if P is in the middle, right? And it has 1, 2, 3, 4, and 5. So we know that chlorine has 7, right? So it needs how many to complete its octet?
1.
It needs 1. So if it shares 1 with phosphorus, and then it shares 1 with phosphorus here, so that's another bond. And it shares 1 with phosphorus here. That's another bond. And then oxygen, it needs 2. So if it takes these 2 up top that it's sharing with it, okay? So then how many do I have around oxygen?
8.
How many do I have around chlorine?
8.
How many do I have around this chlorine?
8.
And this chlorine?
8.
And then what about the phosphorus?
8.
8.
So everybody's happy?
Yeah, but it doesn't accept it that way.
Well, that's because you also need to put the
Electron.
here.
I know.
Yeah.
It still didn't accept it.
Tell them they're wrong.
I know.
Okay. So let me tell you another little story about phosphorus. Phosphorus, because where it's located at, it will sometime like to have 10. And so there's another form of phosphorus, which gives us a more stable version where we have this going on.
Will it let you submit it to see if you got the right answer?
Oh, it's not going to give me the right answer because the more stable version, let me show you the more stable version first. So it's not going to give you, although this is, quote, for our level, an acceptable answer, right? And so I'll have to adjust since I gave you this problem. But a more stable version of this guy is, come on. Oh, there we go. There we go. And then, come on.
You're super glitchy.
Yeah, it is. So phosphorus, since it's in that third energy level, it will sometime, if it allows it to have a more stable form, it will accept 10 around it. It's one of those that is an exception, right? And so this is the version that they're wanting there. Although both versions technically can exist, this one is the more stable version. And the reason why it's stable, let me kind of explain this to you so that you guys know. But I promise you, I will not give you something like this on the test.
I
Or
think, okay,
that, or are you going to correct that so we can put it in the form that we know?
Dr. Henry.
I can't correct it on CHEM-001.
Okay, so
Right.
we just have to make sure we put it in like that.
Yeah, so you're gonna put it in like this. This is your corrected version. Let me explain to you why real quick. So what's gonna happen, okay, is, so each one of these, we're gonna sit there and determine what we call like, it lets us know whether or not the structure is the most correct structure. So the goal is to try to get to a value of 0 for every atom that you're working with. And the way that you determine that is that you go with the number of valence electrons. We know that oxygen has how many valence electrons?
6.
You subtract the number of lone pair electrons. That's 4 right here. And then you subtract the number of bonds. How many bonds?
2.
Okay. So the goal is to try to get it so that everything is at 0 or the lowest number possible. You don't want it to be a 2 or you don't want it to be an 8 or anything like that. So if we look at this one here, Cl, so that's for oxygen. For Cl, number of valence electrons,
5. No, 7.
number of lone pairs,
3.
well, lone pair electrons, all of them together. So if there's 3 lone pairs, there's 6 electrons.
So you do the 6, not the 3?
Yeah,
Oh.
you do 6 electrons. And then number of bonds.
3.
How many bonds do you have with this, just with this chlorine?
One.
Is that a single bond or is that a triple bond?
Single.
So you're talking, yeah. It's a
This one
single-
here,
Yeah.
that's a single bond, right? So number of bonds, 1. So that's going to equal 0. So then all of these here are going to be exactly the same thing. So now look at phosphorus. So we have any lone pairs? Well, first off, how many valence electrons?
5.
5 valence electrons. Any lone pairs?
No.
No, not with phosphorus.
Okay. How many bonds?
5?
That's right. 5 lines, 5 bonds. So does that equal 0?
But I thought you wanted 8. Now you want 0?
Well, no. So this is just to show you that stability-wise, right? So this here tells me that this structure is more stable than this structure, because if we do the same thing with this structure, which is what I'm going to have you guys do here in a second. So let's start off with this one, with the oxygen.
You said that way of figuring out the structure is more what, Dr. Henry?
It tells us the one that is going to be more stable, right? So in theory, both of them can exist, right? But only one of them is going to be stable, stabler than the other, right? So this guy is more stable. So you can see this guy in existence more than this guy. This is going to happen, but it's going to be existing for just a moment because it's not stable.
Is that something you're going to be teaching us in chapter 13?
Well, we're not going to talk about it in that much detail because you guys, for what you guys are doing in your realm at the level that you're at, you don't, it's not needed. You're not absolutely needed to know. If you're going to go into general chemistry, you got to know this. It's going to be a requirement. Right?
Is that going to be something that you are going to want us to know, or is it just going to be?
No, as I told you, I won't ask you this on the exam. It came up in one of your problems, and you're going to have a few problems that it may come up in because I want you to get used to doing Lewis dot structures. I forgot that this is one of those questions that came up in. So I'll have to do a better job of screening my questions.
I have a question.
Dr. Henry, is there another element other than phosphorus that pertains to this?
Yes, so let me show you on the periodic table real quick.
Maybe we can just highlight it. That way we know when we're doing our homework.
Yes, that is a very good idea.
These that I got sent back on, and I'm like,
So, clear. We just move this for right now. Okay, so all of these guys that are in the third energy level, right? So technically all of these guys here can technically do that. So anything that is below here also can technically do that.
so everybody in basically the P level.
In that P level, and it's after that very first one. So these guys up here won't do it. But
Okay.
these guys down here, they're going to try to form, they can form multiple bonds, right?
Okay.
More than just your normal 8, right? So you're going to have some cases where you're going to have more than 8 around them. Like
More than
sulfur
8.
can have 6 around it. 6
Like
bonds.
those,
Phosphorus can have 5 around it. And technically, chlorine can sit there and have 7 to 8 around it. So they're flexible that way.
What about nitrogen? Can nitrogen only have 7 around it?
Nitrogen, no, nitrogen is only going to try to keep 4 bonds. So all of these guys up here, they're going to have 4 bonds. They're going to try their best to have 4, or you're saying 7 electrons around it. It can have an odd number, right? Because remember, we talked about that or have we? We have not talked about it. We will talk about it.
Okay, because that was
We will be talking about those exemptions.
perfect. Thank you.
Is that unable to reach an octet? Was that it?
Yeah, so if you have an odd number of electrons totally, it's not able to reach an octet.
Yeah. We talked about that.
Oh, we did talk about that? See, that's the thing about having so many classes. I start losing track. I'm like, yeah, we talked about it. No, we didn't talk about that. Okay, so I know that, that's a little weird, but this allows us to let us know which one is stable. And as I was telling you, like if we go through this, let's go through that process again. The number of valence electrons that oxygen has,
6.
okay? So how many lone pair electrons does it have around it here?
6.
How many bonds?
1.
1, yes.
Okay, so then that's going to equal -1. So that's already giving us a disadvantage since these guys over here, these were all 0.
Oh, I see.
So let's do chlorine. Number of valence electrons,
7, technically.
okay. Number of lone pair around it,
6.
and then number of bonds,
1. I see.
okay. And then if we look at phosphorus, phosphorus is 5 valence electrons. Number of lone pair,
None.
number of bonds,
4.
okay. So we have a 1 and a -1. So that means that this guy is going to be more stable than this guy.
Dude, Megan and I sat on this problem for like 2 hours today.
Yeah, so you wouldn't have gotten it because of that.
Yeah, Dr. Eric,
Yep.
I think I did it with the 4 single bonds around it.
Yep.
You accepted it.
It accepted it?
Yeah.
Oh, that's good. So, and if you did it with the 5 single bonds around it?
No, with the 4 single bond around it.
Yep. Okay, so I'm gonna put you guys I'm gonna give you some problems to do Lewis dot structures, and then I'm gonna put you guys in groups. Is that cool?
Mm-hmm.
Okay, so let's do. Let's do that one. Let's do this one. Let's do, what was that?
It's N2O?
Yep, that's N2O. Let's do, and let's do, okay, you guys got those?
Only 4 of them, right?
Only 4 of them.
Yes, sir.
Okay, you guys ready? Fabienne, how was it?
Stressful.
Stressful? Come on. What made it stressful?
I was trying to figure out ways to get everything to have an octet, but not all of them have it.
Okay, well, we'll see. We'll see. Everybody back? Anybody got lost?
On the last one, almost a little bit.
You got lost on the last one?
Yeah.
That's on the first
Our
one.
group did a little bit.
Okay. So let's see what we can do. We'll do this as a team effort. Okay, so let's start off
I
with
got
that
lost on
very.
the first one.
You said I got you on the first one?
No, I confused myself, I guess.
Confused yourself? Okay. Well, let's work through it.
Yeah.
Okay, so let's start with CO. How many valence electrons does C have?
4.
So we have 4, and then
4.
oxygen has how many?
6.
So that's a total of 10. We have 10 electrons to work with. Even though it looks like a 16, that's a 10. Okay, so we have 1, 2, 3, 4. And then oxygen has 6. Okay, so we want to show that everybody has 8 around them. So if I do this,
It is a double bond, isn't it?
is it a double bond?
I don't know.
Okay, let's count the total number of electrons. That's 2, 4, 6, 8, 10. So that's a total of 10 electrons. So that meets that rule. How many's around the carbon?
8.
1, 2, 3, 4, 5, 6, 7, 8. 1, 2,
Okay.
3, 4,
How
5,
many's around oxygen?
8.
Damn.
Okay. So it's
Yeah,
a
it was
triple bond.
totally off.
Same.
Fabian, are you there?
Yeah.
Did you get that one?
Oh, I got that. I got something different.
Okay.
2, 4,
So-
6.
What about nitrogen? Or I'm sorry, N2O. So who's going to be in the middle?
Oxygen.
What is the rule?
I think it's nitrogen.
And will be at the middle.
N is going to be in the middle. They're on the same line. Who's closest to a noble gas?
Oxygen.
Oxygen.
Oxygen. So oxygen is going to be hungrier. So oxygen isn't going to want to be in the middle, right? Remember, it's always the weaker guy gets pushed in the middle. So nitrogen is going to be pushed in the middle. How many electrons does nitrogen have, each one?
5.
So 2 times 5 is 10. Plus,
6.
how many?
6.
Oxygen.
6.
So we have total 16 to work with. Okay, so let's go ahead. Let's put these guys in.
Jeez, that was way off.
Okay, we have 6 there. We have 5 here. We have 5 here. So let's see if I go in. Triple bond, single bond. Oh, does that work?
Yeah, it works.
Okay, so that's one way. There's another way that you can
Another
do it.
way, yeah.
So if I went in,
Doubles.
yep, doubles.
Double both sides.
That's right. That's another way. Okay, so that's 2, 4, 6, 8, 10, 12, 14, 16. So that also works there too. And then there's one more way.
Three.
Oh, this is the way I. Okay. This is not the way I did it.
2, 4, 6, 8, 10, 12, 14, 16. So 3 different ways that you could have drawn it. And I would accept it all 3.
Just flip them.
Yep.
Yeah, I was totally off.
So like 3 and 1.
Same.
Yep.
So do you want to form a triple bond more than a single bond?
It depends. So in some cases, there's no choice, but really again, remember when I talked to you about that whole stability part of it?
Yeah.
So if you have an option, you want to try to have the most stable structure as possible, right? That's the best way of going. But sometimes we can't, we're going to have to be a little less stable than we want to be, right? So if you look at all of these, right? So that's 3. So here that would be 4. This guy would be, I'm sorry, this will be 5. This will be 4, and that'll be -1. So this would be, unfortunately, weirdly, this is the more stable one compared to all of the other 2, right? And the only way that we know that is if you guys know that other thing. So,
Yeah.
but again, the goal is to try to get 8. Technically, in reality, you're going to have the ability to have all 3 of these exist. Only one of them is just going to be slightly more stable than the other.
Okay.
Okay. Okay, so our next one, CO2. Who's going to be in the middle?
See,
Yeah.
Okay, so we have what, 4,
Mm-hmm.
and we have 2 times 6.
Mm-hmm.
Oops, not equal. So that's gonna, man, I don't know what I'm thinking today.
equal to.
It's 12 plus 4 equals 16.
I can really add, really. I just don't know that symbol anymore that means equal, you know. Okay, so I have my 4,
Mm-hmm.
and then there's what?
6.
6 there, 6 there. So what do I need to do to make it so that they all have 8 around them?
Double bond.
Double
Would you
bond.
have double bond?
That is correct.
Could you single bond it too, or no?
No, single bond wouldn't work. Let me see. Let me think about this. So if I did a triple on one side and a single on the other, that'll work. So I guess you could do the same thing as we did with the nitrogen.
And triple
See?
bond one side and single bond the other?
Yeah, I guess you could do it that way.
But you don't like it that way.
We got to count it. I always have to count them to be sure. So that's 2, 4, 6, 8, 10, 12, 14, 16. Yeah, so that would work. Yeah, but this one is the more stable one right here.
Okay.
So, Dr. Henry.
Yep.
So, like the CO2 you did, and you do the bond in form of one goes in horizontal and one goes in vertical. You can do it that way, right?
What do you mean?
See the middle.
Draw it on my screen so I can understand what you're saying.
Sorry?
Can you draw it on the screen so I can understand what you're saying?
All right, let me see. Annotate. Okay, like if I have C, do double bond here, have oxygen, then I do double bond here and have oxygen.
You're asking me if you could draw it down like that.
Yes.
Well, technically it would be the same, although the structure itself is going to be a linear structure, and we're going to talk about that. So I wouldn't draw it like this because it kind of sets me up for screwing things up later on, and we don't want that to happen. Okay? So, because we're going to start talking about geometry. So by you drawing it that way, you're saying that they're perpendicular to each other. You're suggesting that they're perpendicular to each other. That's not going to be the case. They're going to form a linear structure. And we'll get into that.
Okay.
Our goal, that's our goal this week. Geometry.
Molecular geometry.
That's right. Okay, so let's see. This guy here, this last one, for the gold. Now, let me give you a hint. In this case, this one isn't going to have 10 around it. It's going to only want to have 4 around it. Or, I shouldn't say 4. It's only going to want to have 8 around it, not 10 around it. So who's going to be in the middle?
Phosphorus.
Okay. And it has how many valence?
5.
So we have 5 plus 7 times 3.
Yep.
So what, that's 26?
Mm-hmm.
Okay, so let's go 1, 2, 3. So Cl has 7 around it. And so that's 1.
The only one I got right.
You got one of them, right?
Right.
So you got one of them right?
Yeah.
Okay. Piece of cake?
Yes.
Okay, so it gets better with practice. That's all I'm gonna say. The more practice you do, the better you'll get. You'll become naturals and you'll be like, Dr. Henry, your structure is wrong. I can already hear Erica and Megan and Eric coming at me already. I hear it already, you know?
Eventually.
Okay. So, do you guys want to do a couple more? Or are you feeling confident?
Let's do a couple more.
Couple more? You want to do something challenging. You know, like this is too easy, right?
No, I just want to get better.
I'm over the dot structure.
Let's do this clear. Trying to
I
erase
get
it.
it. Some of them kind of stumped me. I don't know if it's because I'm overthinking it or also because he said that not all of them are going to be able to add up to, not all of them are going to have an octet. So sometimes I'm like, is this one going to have an octet or is it not? I don't know when those are going to pop up.
Mine's like the double and triple bond. I just want to single bond all of them. I just put the hose.
So I'm going to help you with this one here, because this one's going to be a little complicated. And let's do. Okay. You guys want to do it in groups or do you guys want to do it together?
Do it together.
Okay.
Together.
So let's start off with this first one. Okay. Carbon has how many?
4.
4 valence electrons. We have 2 of them, so 2 times 4.
8.
Okay, and then we have hydrogen. Hydrogen has how many?
1 times 4.
1 times 4. So 8 plus 4 is 12. So I have 12 electrons to work with. So if we go carbon, so who's going to be in the middle?
Carbon.
Just did it, carbon.
Carbon. Okay, so let's go. We'll go 1 there, 1 there. Okay, so we know hydrogen has 1. So that's, and we know that hydrogen only needs 2 electrons to reach its octet.
Yep.
And we know that hydrogen can only form a single bond. So 2 things that we
Is
already
that
know.
always?
Always. Hydrogen can only form a single bond. It can never be in the middle. And it only needs 2 to reach its octet. Okay, so how many is around this carbon here?
4.
8.
Oh, no. 4, yeah,
8 electrons. And then how many around this carbon here?
8.
And then how many around this hydrogen here?
2.
And this hydrogen here?
2.
2. 2.
Piece of cake?
Okay.
That one was all right. That one was pretty easy.
Okay, so let's see about this guy here. So we have that carbon has how many? So we got 2 carbons,
Carbon.
2 times 4,
Oh, that
and we got 4 hydrogens, 4 times 1, And how many oxygens?
2.
And there, how many valence electrons?
6.
Okay. So
Times 2
that
is
adds
12.
up to, see, that's 12.
18.
Is it 18?
Yeah.
24.
Are you sure?
It's more than
Oh, wait.
18.
I
12
lied.
plus 8,
I have 12 here,
24.
I have 4 here, and I have 8 here. So I got 24.
I lied. I forgot to multiply by 2.
Give me the wrong answer. You're just trying to make me wrong, aren't
I was
you?
trying to make sure you're on top of your game.
Oh, okay.
That's why.
You're testing me, huh? Okay, I see.
Yeah.
Okay, so now this is an example of organic chemistry. In organic chemistry, they kind of cheat and they try to give you a hint what the structure looks like. So this guy is going to be a center carbon, and it has 1, 2, 3. So we'll do it like that. Okay. So that center carbon is going to be interacting with this carbon here. So how many carbons? I mean, how many valence electrons? 4, you said?
Yeah.
Okay. So we know that hydrogen can only form a single bond. So that takes care of that. It takes care of that one. Okay. So we're going to have another bond between there. So that gives me my 4 around that guy.
Yes.
Okay. So this here, that center, that guy is going to have an O up top.
Oh, yeah.
And then this guy is going to have and we know that hydrogen is going to be on that oxygen. Okay, so that everybody reaches its octet, what type of bond does this between this oxygen and hydrogen has to happen? Because right now it has 2, 4, 6 around it. So how many does
Double bond.
a double bond?
Double.
Okay.
Oh, I see.
You see it?
Yeah. That's why they're doubles. Okay.
Yep.
So everybody has to have an 8 around them.
Everybody has to have 8 around them except hydrogen, which only
Right.
wants 2.
Right.
Yeah.
I don't ever want to be in the middle.
Okay. And this is acetic acid or vinegar. That's the chemical structure for vinegar.
What do you call it? Acidic acid?
Acetic acid
Okay.
or vinegar for short. Okay, let's do this last one right here. For the money.
You're gonna give us money?
Henry,
What was that? Yes? No, I'm not giving you money. You kind of baked me into that one. Yes, Fabian.
or is that the only structure there is for that one?
You could do a couple of others, right? There are isomers of it. So yeah, you could do technically. There's a couple of others that exist.
For that one, I did it a different way.
Okay, so you can share. Yep. So, but let me give you a hint. Anytime that you see it like this, written out like this is telling you that this is going to form a carboxylic acid, which we will be talking about a little bit later, which means it always has that double bond over here and that OH on this side, and you have that C. This guy can vary depending on what we're talking about. Okay, so, but this is just a hint to help you with your structure. But show me what you got, though. I'm curious.
This one is done.
Should I just draw it out then?
Yeah, just try it out. Don't be shy. We're family.
Let's go.
Yamalet knows. She knows we're family.
So, Mister, can I show you what I got for this last one we're working on?
Yes, you can.
Let me see if I can
You
get
can write it
this
on my
up.
board up there too.
I don't know if it'll let me do it. Oh, never mind. Like, it will.
And those are dots up top, not lines, right?
Yeah, that's what I meant to. I was trying to erase it.
I just want to be sure.
There you go.
Okay, looks good. Okay, Fabian, let's talk about yours, right? Let's count them. Count all the electrons. So we got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. How many do we have?
It's 24.
24. So will that work?
Nope.
No.
No. Say, but that's the reason why we count them all, and we want to make sure at the end. And sometimes you'll notice I'll get lazy, but you gotta keep me on my toes, because Fabian is showing us that, hey, we gotta stay on our toes. Because I've done the same thing before.
I have a question.
Yep.
It's for the HCN Lewis dot structure. So
Yep.
I put it the same way that you did on the bottom, but
Uh-huh.
for the nitrogen, I put one dot on the top and one on the bottom. Does that matter?
It does, because they're usually going to try to form lone pairs. It's better for them to pair up than be individuals. If they're individuals, it's more of a radical, and it's not stable, right? It prefers to be paired up if you can.
Okay, thank you.
Also, I just want to make sure that a lone pair means that that pair of electrons not being shared by another element, correct?
That is correct, Matt. Yep,
Okay.
that is correct.